Hi, everyone. I'm Senrui Chen, currently a graduate student at the University of Chicago, and I'm happy today to share our recent work titled Robust Shadow Estimation. This is a joint work with Wenjun Yu, Zeng, and Steve Flammia, and this work is now available at Archive, and you can find the link at the bottom of these slides. Okay. The focus of this work is on the task of quantum state estimation, basically learning properties of an unknown quantum state. This lies in the central of various applications of quantum information science. So just to name a few, in quantum benchmarking and certification, you will have to estimate the fidelity of some state with regarding to some ideal state. And in quantum simulation, you sometimes will have to create a state to evolve it, and you have to detect the entanglement and correlation functions from that state. And also in some quantum algorithms, for example, the variational quantum eigensolver, estimation of energy of an unknown state would be a central ingredient of that algorithm. In this work, we will focus on estimating an n-qubit quantum state. So you can definitely also consider qubit or even continuous variable system, but here we focus on a more simple but heavily studied case, that is the qubit system. So a standard method to do quantum state estimation is through quantum state tomography, which can obtain the complete information of an unknown quantum state. The problem with quantum tomography are twofold. The first is regarding the sample complexity. So an epsilon approximation of quantum state rho requires no fewer than like 4 to the n times epsilon to the minus 2 samples. And this scales exponentially with the number of qubits, which will render it infeasible for near-term devices, even with like 50 qubits to 100 qubits. And the second problem is regarding the noise. So near-term devices will suffer from various sources of noise, for example, imprecise control, decoherence, measurement without error, and all of this may affect the accuracy of tomography. So regarding these two problems, so on the one hand, regarding the sample efficiency, we need some more sample efficient quantum state estimation protocols. So here I list a few line of research in this direction. The first is that we can try to apply some pre-knowledge to the quantum states to simplify the estimation. So for example, in quantum compressibility, we assume the state has a low rank. And like in matrix product state based tomography, we assume the state has some limited degree of long-term entanglement. And we also have neural network tomography and then many other works. A second kind of research focus on just to extract a certain class of properties instead of the complete information of quantum state rho. So for example, we have quantum overlapping tomography, which can extract all k-qubits reduced density matrix out of rho. And there are quantum shadow tomography, which can like extract the expectation value of m arbitrary to outcome observables, or using samples only scales approximately logarithmically with respect to both m and the dimension of the system d. And also we have a shadow estimation, which is like a more practical version of the shadow tomography. And we will discuss about it later. Okay, on the other hand, regarding noise resilience, we know that noise in quantum circuit may affect the estimation accuracy, especially for near term, where fault tolerance are not currently available. And the idea of error mitigation is like a new paradigm designed for NISQ devices. It basically makes use of noisy circuit components, but introducing some extra calibration rounds of experiments and use classical post-processing to obtain like the error mitigated result. So Something that is more relevant to our work is called mitigation for measurement readout error. Okay, but there is still much left to explore how to apply like error mitigation to the quantum state estimation task. Okay, so we've reviewed the two problems of quantum tomography, and the contribution of our work is exactly we propose a new method called RShadow, which is a sample efficient and noise resilient quantum state estimation protocol based on the shadow estimation scheme in this HKP 20. So our methods only requires the noise to be gate independent, time stationary, and Markovian. But we do not assume any specific model or any pre-knowledge of the noise and also of the state. So we can deal with highly entangled noise, something like that. And also our method is experimentally friendly in the sense that it can be readily implemented on many current experimental platforms for a wide spectrum of applications. Okay, so now let's come to the details. So in order to introduce our work, we'll first introduce the shadow estimation work. So this is from this paper, predicting many properties of a quantum system from very few measurements by Huang, Kun, and Preskew, which is published in Nature Physics 2020. So by the way, all the reference in this presentation can be found at the end of this talk and also in our paper. So the task of shadow estimation basically they take IID copies of an unknown state row as input, and also there's a set of M observables to be predicted, but this observable can be specified later after the experiment, and we want to give an estimate of the expectation value of all the observables. So here we focus on linear functions, but in their paper, nonlinear functions can also be predicted. So the idea of shadow estimation is basically for every copy of row, we use a randomized measurements to calculate an unbiased estimator row hat of row, which is called a classic shadows. Then we can compute any properties using this classical shadow row hat, and we take an average over different copies. The main contribution of this work is they prove that this method can be highly sample efficient for a certain class of observable O. And this is so a demonstration of the quantum circuit of the shadow estimation protocol. So for a single copy of row, the first sample a unitary gate from some group G, and then apply a Z basis measurement to output a cat B, where B is a computational basis state and B is actually a n-bit binary string. And then they do some classical processing to calculate the classic shadow row hat. And the classical processing follows in this way. So basically, they first do a unitary dagger in classical processing, and they apply a channel M inverse. And the channel M is defined as an expectation of the channel demonstrated here, U, MZ, and U dagger. And you can see that this channel is like, you can calculate it theoretically if you have specified a group G that you are sampling this unitary U. And it is immediately to see that in this method, the classical shadow row hat you get here will be an unbiased estimator of row, because the M inverse exactly like inverse the effect of all the randomized measurement applied here. So obviously every estimation you get with respect to this row hat will be unbiased with the estimator with respect to the original unknown row. Okay. And here I list their protocol more rigorously. So basically, you do a randomized measurement, and you calculate the classical shadow, and you estimate all the functions with respect to this classical shadow. And finally, you take an average of all the estimates you get for different copies of this state. Actually, in their original paper, they instead of using average, they're using something called median of mean, and there are some subtleties, but I will not elaborate here. Okay, so now we care about the sample complexity of this method, and this is a theorem in HKB20. So classical shadows of size R, which means you use R copies of the state rho surface to predict arbitrary M linear target functions to up to accuracy epsilon, given that R is proportional to epsilon to -2, and also logarithmic of M, and also the maximum value of something called a shadow norm. And the shadow norm is a function depending on which unitary group are being used here. So for example, if you sample the gates from the n-qubit Clifford group, then the shadow norm is bounded by the so-called Hilbert-Schmidt norm. And for example, if you want to estimate the fidelity of a state with respect to other pure state, then this Hilbert-Schmidt norm will be a constant, and this method will be highly sample efficient in the sense that it is independent of the system dimension D. And also, if you are using the global Clifford group, which is an n-fold tensor product of single qubit Clifford group, then the shadow norm will be upper bounded by 4 to the key times the infinite norm. Here, the key is a locality parameter of the observable O, which means this observable O is only non-trivially supports on k qubits. So the implication here is that you can efficiently estimate any local properties of a quantitative rho in a highly efficient manner. Okay, so this is a review of the original shadow estimation paper. And now let's consider what experimental noise will cost in this process. And okay, so recall the circuit of shadow estimation. We see that in realistic experiment, both the quantum gates U and the measurement MZ will be subject to noise. And we remark here that, so first, the U dagger and M inverse is done in classical computer, so there's no noise. And the state rho here, because we are doing a quantum state estimation process, so we do not care about how rho is prepared, and so rho does not have a state preparation error because everything in rho is what we want to estimate. Okay. So now let's simplify the noise model a little bit. So the noise U can be decomposed without loss of generality as U followed by a channel lambda U. And similarly for the measurement MZ, you can decompose it with a noise channel and a noiseless measurement. And then you combine these two channels into a big channel called lambda U. Okay. Now we can see the problem of noise. So originally, we claimed that the classical processing M inverse would completely inverse the effect of the randomized measurement. But here, because we have a noise channel here, now the M channel becomes M tilde, and cannot be precisely inversed by this theoretically computed M inverse because we do not know lambda U here. Okay, so in general, there's no possibility for us to identify lambda U from the unknown state rho. But we can introduce the idea of calibration. That is, we can experiment instead of on rho, but on some probe state rho naught in order to characterize this M tilde. And then if we characterize this M tilde, we can eliminate its effect by post-processing. So this is exactly what we've done. We show that we only need to have a fixed probe state, which is the cat 0, which is the basis, the one computational basis state. Yeah. And of course, this time, if we want to prepare some probe state 0, then this preparation is definitely subject to state preparation noise. So here is the circuit of our robust shadow estimation protocol. Our protocol is contained of a calibration stage and an estimation stage. So for the calibration stage, we prepare some state row, some state 0, and we do the randomized measurement. And using this result, we can do some calibration functions in order to have an estimation of the M-tuned channel depicted here. And after this calibration, we can do the standard shadow estimation protocol, but with the classical processing slightly modified. This modified classical processing channel will now eliminate the noisy randomized measurement here and give us an unbiased, approximately unbiased estimate of the classic shadow, given that you've done enough round in the calibration. Okay, now to show the correctness of our protocol, we will have to have some assumptions on the noise. So we have two assumptions. The first is that the preparation of the state 0 has high fidelity. The second is that the noise channel lambda u we consider here must be gate independent, time stationary, and Markovian. This is sometimes called the GTM conditions in the literature. And this will renders the channel lambda independent of the choice of u and also independent of the time parameter. Okay, let me make some remarks here. So firstly, the preparation of state 0 is relatively easy on many current experimental platforms. And regarding the GTM conditions of the noise, at least for local Clifford groups, it is relatively easy to achieve in current experimental systems. And also, if we are considering the context of readout error mitigation, that is, we only consider the error at the measurement site, then this gate independent condition will immediately be satisfied. Okay, so let's go on. So under these assumptions, the circuit can be simplified like this. Okay, so note that we assume that the state 0 here is perfectly prepared, but we have some analyze in our original paper that if the state is prepared with a small infidelity, then our result will still hold. Okay, I will refer interested reader to read our paper. Okay, so now let's see what is really interesting happening here. So here now the lambda is independent of u. So the M-tuned can be right in this way. And you can immediately identify this as a unitary Turing of the channel MZ following lambda. And by some techniques called Shor-Weil duality, we can write this M-tuned into a linear combination of the projector pi lambda. So projector pi lambda is a projector onto the irreducible representations of the group G we choose. And I will not elaborate on more mathematical details here, but one thing we need to notice here is that now, thanks to this unitary Turing, instead of characterize the whole channel of lambda, or in order to characterize a whole quantum channels, we only need to characterize some noise parameter f lambda, the number of which is only dependent on the number of irreducible representations of the unitary group we choose. Okay. So now it comes to our main protocol, RShadow. So this is divided into two parts. The first is called a calibration procedure. So in the calibration procedure, you have to decide the unitary group of unitary gates, and you try to characterize the channel M tilde, that is to characterize the noise parameter, F lambda. So basically what we're doing is that we prepare the state 0 and we apply randomized measurement, and then we use a subroutine called noise estimation to get an estimate of all the noise parameter F lambda. This subroutine will be defined later. And we use a single copy to get a single copy estimate, and then we take an average over all samples to get a final estimation of the noise parameter and also of the noise channel F tilde. So this whole protocol is extremely similar to the standard estimation protocol, but we are doing a different classical post-processing. Okay. So after having an estimate of the channel M tilde, you can now do the estimation procedure. And the step is similar to the standard shadow estimation. The only difference appears here. So here, when calculating the classical shadow, you do not use the M inverse. You use the M hat inverse that you estimate in the corresponding calibration procedure. Okay, so let's talk about the construction of the noise estimation procedure. Recall that every noise channel M tilde actually here is characterized by a set of noise parameter F lambda, and given a specific group G, we should have a specific method to calculate the set of noise parameter. In this work, we focus on the following two cases. The first is a global Clifford group, and we are able to derive that. So the first note is that there's only one non-trivial irreducible representations of the n-qubit Clifford group, and we're able to calculate that the noise parameter can be calculated with this function in our original paper. Second, for the local Clifford group, tensor product of single qubit Clifford group, we also derived a function method to estimate the noise parameter. So now the noise parameter scales as 2 to the n. And what's really interesting here is we can use a single copy to simultaneously extract all these 2 to the n noise parameter. And this is quite similar to recent work by Steve and his collaborators on efficiently learning a polychannel. Okay. And also, we remark that in practice, we do not actually have to calculate all the 2 to the n number of noise parameter, because if we do that, the computational complexity will be really high, even though the sample complexity is still favorable for us. Okay, so for more details, we refer the reader to read our paper. Okay, so now we can talk about the performance of our protocol. Let's first talk about the protocol using global Clifford group. So regarding the calibration process, we have the following result. If the number of calibration samples satisfies that R is proportional to epsilon to the -2 and Fz lambda to the -2. Here the Fz is a function we called Z basis average fidelity of the noise channel lambda, which is, you can say that quite similar to the well-known average fidelity of a channel lambda. So if we can reach this sample complexity of calibration, then the estimation stage will give an approximately unbiased estimate overall. So this sample complexity, you say that if the Z basis average fidelity of the noise is high enough or is lower bounded, then the whole sample complexity will be really favorable for our to do the calibration. Okay, but you may still ask that then what is the sample complexity of the estimation process? So here comes our theorem 2, which considers the total sample complexity. So if the number of calibration samples and the estimation samples satisfy this function respectively, then we can estimate m arbitrary linear functions such that every observable is bounded by can be normalized in their Hilbert-Schmidt norm. Then we can estimate all of these functions simultaneously up to accuracy epsilon1 plus epsilon2 with high success probability. And you see that if the noise level can be bounded here, then the whole protocol basically can retain the high sample efficiency of the standard shadow estimation protocol. So basically, this is our contribution. We like give a robustified version of their shadow estimation protocol, and this protocol comes with a very little overhead of sample complexity, but it comes with a provable noise resilience. Okay. Okay, and also we're interested in using the local Clifford group, which is more easily implementable. And we see that the calibration procedure will have similar result, but with a extra factor of 12 to the k. When the observable we want to estimate our k local, this scaling can still be really favorable for small k. And we remark here, this result do not require uncorrelated noise model. So even if the noise is highly entangled, we can still use in these local Clifford groups to calibrate this noise. So basically, this is thanks to the fact that local Clifford turning or even Pauli turning can turn a highly entangled noise channel into a very simple Pauli channel, and then we can calibrate it. Okay. And regarding the total sample complexity of this RShadow using local Clifford group, here due to some technical difficulty, we can only derive the result assuming the noise channel is in a product form, a single qubit product form, that is, there's no crosstalk. And if this is satisfied, we know that the total sample complexity is like still proportional to a constant factor to the k and proportional to log m for all observable, that is k local. Okay, but we remark that even if the noise is highly entangled, we can still get the correct result, but we don't have much to say about the sample complexity of the estimation process. But later we will see numerical examples about correlated noise in this local Clifford region. Okay, now finally we can see some numeric examples of our result. So our first numerics simulation is that we create a 50-qubit Ising model at the critical point. And we want to estimate the 2-point ZZ correlation functions of this Ising model. But we assume that in the measurement, we have a bit flip error rate of 5%. And we compare the standard shadow estimation with our robust shadow estimation using global Clifford group. And here's the result. This is the absolute value, and this is error. We see that our robust shadow estimation algorithm can achieve a much lower error than the standard shadow estimation, which do not calibrate this bit flip error rate. The first experiment is using the local Clifford group, and the second experiment, numeric experiment, using a global Clifford group. We create a 10 qubits GHZ state, and we want to estimate the fidelity with respect to an ideal GHZ state, but with respect to bit flip error, depolarizing error, and amplitude damping error. So here's the result. Still, we say that when the strength of the error grows larger, the standard shadow estimation algorithm will deviate from the true value, but our robust shadow estimation algorithm will basically return the true value, which is 1. Our last experiment consider coherent noise and also crosstalk. We create a 5-qubit GHZ state, and we want to estimate the 2-point ZZ correlation function. We take an average of that, and the true value is definitely 1. And here we consider noise Hamiltonian, which is like a coherent rotation, and also rotation with crosstalk. And we see that even against this coherent noise, our robust shadow estimation can still return fairly good performance compared to the standard shadow estimation method. Here we present some additional numerical results about gate-dependent noise model. The task we consider here is to estimate the H2 molecule's ground state energy using local Clifford group-based scheme. So to consider a realistic implementation of the shadow estimation scheme on experimental devices, we decompose every single qubit Clifford gate into a series of concatenation of pi/2 rotations along x, y, or z axis. So the rotational generators will look like this. So the first noise model we consider is a pulse miscalibration error, which basically describes that, okay, there is some fixed uncharacterized perturbation. So the rotational generators will look like something like this, where delta 0 is a fixed Hamiltonian, and is the same for all the rotational generators. The second kind of error we called over or under rotation error. Basically, this describes that due to imperfect pulse control, the actual rotation is not pi/2, but pi/2 plus some delta, where delta is Gaussian random variables. And we show in our paper that both noise model is actually gate-dependent noise model. Okay, so here is our result. So just to fix the parameter, we encode H2 molecules with Bravik-Kitaev encoding into 4 qubit. And the standard shadow estimation protocol using 10,000 samples, the robust protocol using 30,000 samples for calibration, and then 10,000 samples for the estimation stages. So we can look at these two pictures. So for the first figure, it basically shows that for the pulse miscalibration noise, robust shadow estimation can have a very good accuracy until the noise level become extremely large, and it greatly outperformed the standard estimation scheme. And for the random over rotation noise, robust shadow estimation seems to give perfectly accurate estimate, even when the noise intensity becomes extremely large. We also comment here that for our parameter setting, when the noise level is around the 0.1, it is already fairly large for a practical experiment. So this experiment provides evidence that our scheme can still be very good at performance, have good performance for realistic gate-dependent noise model. So this is the end of our talk. To sum up, we propose robust shadow estimation as a sample-efficient and noise-resilient quantum state estimation scheme. From the practical viewpoint, this is a robust and fast protocol to predict many properties of a large-scale quantum system on current experimental platforms. From a theoretical viewpoint, this work is a combination of efficient quantum state estimation scheme with a field of error mitigation. It also uses ideas from efficient polychannel estimation. And here are some open problems. Can we have an experimental demonstration? Can we consider operations other than Clifford group? Can we have a rigorous analysis on gate-dependent noise? And also, can we extend the scheme to quantum channel estimation or QT system and even continuous variable systems? So thank you for your attention.